Hello students, I am Jasbir Singh, Assistant Professor of Physics, Pandit Nikriram Sarma Government College, Rohtak. In this lecture, we will be discussing operational amplifiers and its applications. We will see a brief overview of operational amplifiers and its applications. After the lecture, you will be able to understand what is an operational amplifier, its block diagram, its ideal conditions, and its practical properties, and many of its uses. So, let us begin the operational amplifier. An operational amplifier is a multi-stage direct coupled high gain negative feedback amplifier. A negative voltage shunt feedback is provided to stabilize voltage gain. Generally, these op-amps are available as integrated circuits, that is ICs. The main use of an op-amp is to amplify AC or DC input signals. This was initially designed to perform basic mathematical operations such as addition, subtraction, multiplication, differentiation, and integration, and hence its name is operational amplifier because it performs mathematical operations. Now its application have been extended to use in active filters, oscillators, comparators, voltage regulators, instrumentation and control systems, square wave and pulse wave generators. Generally, these are manufactured with integrated resistors, capacitors, transistors, and diodes, thus making it an extremely compact, multitasking, low cost, highly reliable, and temperature stable integrated circuit. So we can say it is a very versatile circuit which can perform a variety of functions such as mathematical functions, addition, subtraction, multiplication, differentiation, integration, and also it have uses in active filters, oscillators, comparators, voltage regulators, square wave and pulse generators, and it is available in highly useful integrated circuits. So it can be used in a variety of ways. An ideal op-amp have the following properties or the characteristics. The first is its input resistance is infinity. So it provides infinite input resistance. The second property is its output resistance is 0. The third one is its voltage gain is infinity with the bandwidth also infinite. It is perfectly balanced, that is, when the input voltages V1 and V2 are equal, output is 0. Moreover, all these characteristics do not drift with temperature. So these seems very magical properties. All the required properties then we can imagine are available in these operational amplifiers, such as input resistance is infinite, so it can effectively sample the signal voltage. Also, no current flows through the input terminals, so it does not unnecessarily load the signal source. Its voltage gain is infinite, and also its output resistance is 0, so that we can effectively use this output. Also, its bandwidth is infinite, so theoretically it can amplify signal of any frequency, and also it is perfectly balanced. That is, when V1 is equal to V2, then its output is 0. This characteristic is required to cancel any noise. So this is also a very useful characteristic, and also its characteristics do not drift with temperature. So we can say that temperature variations are also not a problem in this case. You may now wonder whether these ideal characteristics are really possible, or how far an actual op-amp fare in this comparison. So these are some practical values of an op-amp. The open loop gain of a typical op-amp is about 10,000. So it is very high open loop gain. But the closed loop gain is much smaller, because we do not need so much of amplification, so we use negative feedback, and closed loop gain is much smaller, and practically we can select any gain from 1 to 10,000. As its input resistance is concerned, it is of the order of several mega ohms. So its input resistance is really high. It's not infinite, but it is very high. Also, its output resistance is very small, which is less than 100 ohm, or maybe you can say 50 ohm also. But effective output impedance in closed loop is also very small. So we can say that all the characteristics of an ideal op-amp are nearly possible in a practical op-amp also. So we have nearly matched all the ideal characteristics that we have discussed earlier. So let us now see how we represent it. That is, what is the symbol of operational amplifier. It is shown by this triangle type of drawing. It has two inputs. One is called inverting input, the other one is called non-inverting input, and we have one output terminal shown by V. Now let us take a look at its block diagram. In the block diagram, we can see it is generally made up of four different stages. The first stage is a differential amplifier which is dual input balanced output differential amplifier. It means it has two inputs and two outputs. It decides its input impedance and is called input stage. Then the second stage, which is also called the intermediate stage, is also an differential amplifier. This is a dual input unbalanced output differential amplifier. It is unbalanced because it has only one output terminal. Both of these differential amplifiers basically gives almost all of its magnification or amplification. The third stage is called level shifting stage, and it is an emitter follower using constant current source. As its name suggests, it is emitter follower, so it does not amplify, but it shifts the signal level. And what does it mean? That we can shift the signal so that its base is 0. In the previous stages, the signal shifts itself from the 0 level, so it is necessary to control this shifting, and this is done with the help of this level shifting stage. Then finally we have the output stage. This is a complementary symmetry push-pull amplifier. It is the output stage and it decides its output impedance. So this is the block diagram of an operational amplifier, and in this we have shown two inputs. One is non-inverting input, other one is inverting input, two bias voltages VCC and VEE, and an output. In its symbol, however, we do not show these bias voltages, and we only show two inputs and a single output, as you can see at the top of the diagram. So this is the block diagram of operational amplifier and its four stages. Let us now see its basic connection modes. It is operated in two main modes. One is called inverting amplifier, the other one is called non-inverting amplifier. Basically, if you apply the signal to the non-inverting terminal, which is shown as plus terminal, then it is called a non-inverting amplifier. The other terminal, which is inverting terminal, is grounded. On the other hand, if you ground the non-inverting terminal and apply the signal at the inverting terminal, then it is called inverting amplifier. You can see a non-inverting amplifier amplifies the signal in phase with the input. On the other hand, an inverting amplifier amplifies the signal but changes its phase by 180 degree. So that's why it is called an inverting amplifier, because it inverts the input signal. So let us study these one by one. First, inverting amplifier. This is the basic circuit of an inverting amplifier, in which the non-inverting terminal, that is plus terminal, is grounded, and the inverting terminal, which is minus terminal, is given a negative feedback via a feedback resistance RF. The input is applied through resistance R1. As you can see, the output is minus RF by R1 V1. So its gain is minus RF by R1. That is the ratio of two resistances. There is a very interesting concept of virtual ground in this inverting amplifier. As I have already told you that both the input terminals are at same potential, that is V plus and V minus are at same potential. So the non-inverting terminal, that is plus terminal, is grounded. Therefore the inverting terminal is also at ground potential. This is called virtual ground. It is so because no current flows in the input terminals of an op-amp. Therefore the current flowing through the two terminals IN is 0, and this is very useful concept which you should always keep in mind while solving any op-amp circuit. As no current flows in the input terminal, therefore we can say that the current I which flows through the impedance Z also flows through the impedance ZS. Now let us take a closer look at this concept of virtual ground. We will see how this virtual ground is effectively maintained for a real op-amp. For a real op-amp, typical open loop gain is about 10 to the power 6. So its output voltage is A times V difference. V difference is the differential voltage applied at the inputs. That is, V difference is the V plus minus V minus. Let the output voltage is 10 volt, which is a typical value. Then this V difference will be 10 microvolt, which is a very small value. So we can say that with this V difference is negligible and V plus minus V minus is 0, and we can say that both the terminals are at same potential. So this is the reason why we call that inverting terminal is at virtual ground. Or in a more general way, we can say that both the input terminals are at same potential and they are short circuited. So while solving an open circuit, you should always keep in mind two concepts. One is that of virtual short circuit, which says that both the input terminals are at same potential, and the other one is that no current flows into the inputs or out from the inputs. You will keep in mind both thumb rules and you will be able to solve any op-amp circuit. These two very simple rules are the most important thing you should remember of an op-amp. So let me repeat it once more, that the first rule is both the input terminals are at same potential, and the second one is no current flows through the inputs. With these general rules in mind, let us start exploring the op-amp circuits. The first very important op-amp circuit is an inverting operational amplifier. In this circuit, as you can see in the figure, the op-amp is connected in inverting mode. The voltage, that is signal voltage, is applied to the inverting terminal through a resistance R1. Negative feedback is provided through another resistance RF, while the non-inverting terminal, that is V plus, is grounded. As you know, we will use the two rules I just discussed about. The first rule, that no current flows into the input. So the I1 current that flows through R1 also flows through RF. That is, the current I1 and IF are the same. And the second concept, that both the input terminals are at same potential. As we have grounded the V plus terminal, so V minus terminal is also at virtual ground. So V plus is 0 and V minus is also 0. Now let us calculate I1. I1 is equal to the voltage drop across the R1 divided by R1. The voltage drop is Vs minus V minus. As V minus is 0, that is I1 is given by Vs by R1. Now let us calculate IF. IF is equal to V minus minus V naught divided by RF. Again, V minus is 0. So IF is equal to minus V naught by RF. As I1 and IF are equal, we can say Vs by R1 is equal to minus V naught by RF. Rearranging these terms, we can write V output is equal to minus RF by R1 into Vs, or we can say V naught by Vs, that is output voltage by input voltage, which is also the closed loop gain, is equal to minus RF by R1. The next circuit we discuss is non-inverting amplifier. In this circuit, the input signal is provided through the non-inverting terminal. a negative feedback is provided just as the same as we have provided in a inverting amplifier. But R1 is grounded and the input signal is provided through the non-inverting terminal. That is the only difference. So let us calculate the closed loop gain in this case. In this case also, the negative feedback is provided through the same two resistances R1 and RF, and the signal is provided through non-inverting terminal V positive. Now, as we can see, V plus is equal to Vs, that is signal voltage. As both the inputs are virtually short circuited, so V negative is also equal to V plus. Now, from the voltage divider circuit, we can show that if output voltage is V naught, then V negative is equal to R1 by R1 plus RF into V naught. This can be derived from simple voltage divider circuit method. And V negative is equal to Vs. So putting this value, we can calculate the AVF, which is closed loop gain, and equal to V naught by Vs is equal to R1 plus RF by R, or 1 plus RF by R. So closed loop gain in this case is 1 plus RF by R. So closed loop gain is dependent only on these two resistances in both the cases, that is inverting as well as non-inverting op amp. The closed loop gain is dependent only on R1 and RF. So let us summarize what we have learned. In the case of an inverting amplifier, the output waveform is 180 degree out of phase, and its closed loop gain is given by AVF is equal to minus RF by R1. On the other hand, in the case of non-inverting amplifier, the output and input are in same phase, and its closed loop gain is given by AVF is equal to 1 plus RF by R1. The minus sign in the closed loop gain of inverting amplifier signifies the 180 degree out of phase output. And also it should be noted that the closed loop gain only depends upon the two resistances, that is R1 and the feedback resistance RF, and no other value comes in the expression. So that's enough for today's lecture, and before leaving, let me remind you the two golden rules that I have stressed so much. The first rule is that no current flows in or out of the inputs, and the second rule is the op amp tries to keep the inputs at the same voltage always. So students, always keep in mind these two golden rules, and you will never be puzzled at any op-amp circuit. That's all. Thank you.